So, I'm going to be looking at a couple of amplifiers today, this evening, or this afternoon, wherever you are in the world. And we're going to be looking at, to see whether these cheaper, smaller 4-channel amplifiers or mono amplifiers are actually worth the repair. Are they worth your time repairing? Are they worth the parts to repair these smaller amplifiers? So, the amplifier which I have to look at first is a JVC. A JVC. Now we know about JVC on my channel if you've been following me for a long time. So this is a JVC, this is a KSAX3204, which means fuck all to me because I've never seen this amplifier before in my life. And it has a sticker on the front which says, "Will not switch on, blows fuse." So, what does that tell us? Can anybody tell us what that can anybody tell me in the live chat, what does that mean? So, let's see, why is it blowing fuses? We can see why it's blowing fuses by taking our multimeter, putting it onto diode beep setting, and beep beep beep, popping it on the ground and the plus 12. Okay, interesting, that's strange. So, usually when an amplifier won't stop blowing fuses it's because the power supply is dead. In this case, the power supply actually seems to be okay. So there's two possibilities here. Either the power supply is okay because we have the charging the power supply rail caps, or the power supply is so dead that it's actually blown the FETs into smithereens, and they are no longer making a short circuit anymore. They're actually just open. Okay. So there's nothing that's nothing looks like smoked or burnt in there. It looks quite clean. Yeah, look at all that space. You've got space for a party in here. We're gonna have a party inside this JVC. Probably got a dead output, so... Is it this channel that's dead? No, it's not this channel that's dead. Is it this channel that's dead? No, it's not that channel that's dead. How about this one? No, it's not this channel that's dead. So it must be, by process of elimination, the last channel. Huh? Say what? What the fuck? So that's not dead either. So we don't seem to have any dead transistors, and they're not FETs. These are not FETs, these are transistors, because it's a class AB and I don't think it's using MOSFETs. So okay, let's have a look at the power supply MOSFETs then. So these didn't seem to be presenting a short circuit. No, we have charging power supply rail caps, so that they're not dead either. No, they're not dead. Whoa. Why is this blowing? Alright, so obviously this could be the customer wiring it backwards or something. So the customer could be doing something very wrong here. We have a fuse in here that's a 40 amp that's not blown. So let's apply some power to this. this could actually probably work fine. I wonder if this works fine. Okay, interesting. So nothing's blown, but the power supply doesn't work. So what I'm doing is what I'm going to do is, just for you guys on the live stream, I'm going to probe the gate first. So this is what the gate drive looks like. Okay, a bit wobbly, but it's fine. The gate drive looks okay. On the output of the MOSFET, however, we have this. So now we're on the second MOSFET. The second MOSFET gate drive looks okay. Second MOSFET output looks like that. Let's go over to the other side of the board and check the other one here, the other gate. So the other gate looks okay, but the power supply drive looks like this. And the fourth one, last one here, the gate drive looks like this, but the output looks like this. Okay. The output of this power supply is meant to look like a nice big square wave on the screen here. It's meant to go down to ground and up to 9 volts and down to ground, and it's currently not. What it's doing is it's just oscillating around the 9 volts rather than going back down to ground. If we look on the output section, the outputs are not being charged, so the power supply is not working. This square wave here that you see is not enough to drive this transformer. I wonder if we've got a shorted transformer that's causing that. Sometimes a shorted transformer can make it look like that. The transformer looks like it's quite well seated though, so I don't think we have a problem with the transformer here. Okay. So let's because obviously to repair this amplifier either way we've got to take it out the case. So let's start undoing the screws here, and let's find out whether there is a 494 on the bottom of this board in SMD format, or whether it's using some other janky ass method to generate the switching frequency. So Aha! So my guess was right. We do have... Holy moly! So what once looked like a simple amplifier that had nothing in it has suddenly become one of an extremely complex amplifier. So this area here is the bit that we're interested in. So here we have a surface mount TL474. TL494 even. TL494. Surface mount TL494. And we have the driver transistors on the back here probably as well, which are most likely to be... where's my tweezers gone? Take some spare tweezers. So yeah, the drivers are probably this one here perhaps. This one here perhaps. Perhaps also this one over here. Or the drivers could be on the other side of the board and they could be through-hole components. So... let's power her back up. Let's apply some power again, and we need to be careful because by applying power to this, these power supply MOSFETs are going to be getting quite warm because they're not being driven properly. You see? So we do need to be careful not to keep this thing on for too long. Okay, so I'm just going to check, see how hot these things are getting when I drive that. Yeah, so they get warm quite quickly when I do that. But let's see, because if I feel for heat, if two of them are getting hotter than the other two, then that tells me something. So, wow, these two are getting hot very quickly, but these two are staying cold. Okay, so the issue has been isolated to this side, yeah? So although the drive wave looks the same on all four of these, yeah, the ones that are getting hot are these two here and not these two, which means that the issue is on this side. Let's have a look at the drive wave on this side. Drive wave looks good here. Yep, the drive wave looks pretty good there on the driver. So maybe it's not the driver, maybe it is a shorted transformer winding. Perhaps it's a shorted transformer winding. Let's just check that the 494 is healthy. So what have we got? Pin number 5 should be a nice sawtooth wave. Yes sir, it is. Nice looking sawtooth wave there. See, that's what the sawtooth wave should look like. From yesterday, I was showing you the... was it yesterday? I think it was yesterday. I was showing you a nasty looking sawtooth wave on one of the amplifiers I was working on. Pins 9 and 10 should be a nice looking square wave. Yes sir. Yes sir. Should have 5 volts on pins 13 and pins 14. Yup. And yup. So we do have 5 volts on 13 and 14. So the chip is in the correct operation mode. So that's not the problem. So it looks like they're being driven okay because the drive waves look okay. So we are looking for some other issue somewhere else. So the next thing I'm going to do is I'm going to actually measure the inductance on the transformer. Because I wonder whether the transformer is at fault here and it's causing a short circuit. Because the wave there on the output of the MOSFETs looked very similar to the wave I've seen before when we have a shorted transformer. So we have 353 microhenries on that one with a 0.2 ohm resistance. The capacitance of this wind is 10.1 nanofarads. Okay, so that one's fine. That one's not shorted. Let's try the second primary wind. So we've got 350 microhenries and 10.1 nanofarads. So that's almost identical to the first wind. So that is also going to be fine. Now let's check the secondary winds. So the output wind, we have 352 microhenries. That's also fine, 0.3 ohm. And the last one here, the last wind, we have 351 microhenries. So the transformer is not the problem either. The transformer is not the problem either. Okay, so by process of elimination then, let's try removing the rectifiers. And we are going to try and remove the rectifiers, which are these two things here. And these two things are what connect the power supply section to the output section. And by removing the two rectifiers, we can isolate the two sides of the board to work out whether it's the output section or the power supply that is the issue. So yep, we have removed the rectifiers, and let's power this back up then and see whether the power supply is happy or no. There we go. Look at that. So all of a sudden we now have a proper power supply switching wave. So there's something wrong then with either the rectifiers or with the output section. So the first thing I'm going to do is check the rectifiers. It shows up in the tester as a set of 2 diodes, which is correct. Yeah, see that? That's how it's meant to look, because we've got 2 diodes, they're both facing towards each other. It's fine. So that probably means that we've got a fault on the output section somewhere. And for the power supply to be getting hot like it did just then, I imagine that there is a problem. There's a dead short somewhere. A dead short somewhere. Because for the power supply to be getting that hot, there must be a dead short somewhere. So no shorted drivers either. Nothing obvious here. How about capacitors? Let's go and check some capacitors. So the capacitors are 1, 2, 3, 4 on the board. Aha! Hang on a minute. Okay, so on this rectifier we have a dead short between these, a dead short between these, and a dead short between these. Whereas on this rectifier we have a dead short between these, which is the we're just reading the transformer wines, but we don't have a dead short between that and that. That's capacitors charging. So that is our issue. There is a short circuit somewhere around this area, near where the this rectifier is. So I wonder if it's these capacitors here. Let's have a look. So you see this here. We've got a couple of very small capacitors on the board here. CY1 and CY2, like that. Okay, and there's a short circuit across these. I don't think that that's meant to be the case. Let's check these rail capacitors. So we've got the 2 big rail capacitors here. Let's check, see if there's a short circuit on between these. Aha! Okay. Yes, there is. Yes, there is. So one of these main rail capacitors here has a dead short circuit across it. See that? Dead short circuit across this main rail capacitor. So that's either the main capacitor that's causing that, or it's these 2 small, tiny surface mount capacitors. So the most likely thing is going to be the surface mount capacitors, because they are more sensitive. So I'm going to turn my hot air soldering station on, and we're going to remove those surface mount capacitors and see whether the short circuit goes away. We're getting somewhere with this board. Looks like the board's about to snap. Yeah, literally. Yeah, this board is made of cheese. It's a fine French cheese. It's a JVC. It's a JVC cheese. So, let's see. Has removing those 2 small SMD capacitors resolved our issue with the short circuit? Has it solved our issue with the short circuit? No, it has not. Okay. It has not resolved our issue with the short circuit. So the SMD capacitors are not to blame. Let's just make sure that they are not shorted anyway by putting our multi-winch on them. So they're not to blame. So we're starting off with the smallest, most likely part to blow, and it's not that. So we're going to move on to the next most likely part now. So it's either going to be the large rail capacitor that's actually blown. If it's not the large rail capacitor, then it's going to be something that is connected to it, like well. Now, if we have a look at the board, let's just use some visual inspection to see what else could be causing the issue. So we've got a short circuit across this capacitor here. So these two pins here. Let me zoom in a little bit more, if it will zoom in while still staying in focus. Yep, we're looking good so far. So we've got a short circuit across these 2 pins. This is one of the rail capacitors. So what else is going across these 2 pads? We've also got some very small, quite high value resistors, and these are the pull down resistors. So when the amplifier is turned off, the voltage in the capacitors will discharge slowly through these resistors, which makes the amplifier safer to work on. In terms of operation, it actually makes no difference whatsoever. It's actually better to not have these there in the first place, because then the power stays on the rails, and when you turn the amplifier on next time, it's not going to work so hard to charge the rail caps again. So I wonder whether these resistors are damaged at all as well. So the only way to find that out, because there are so many different components in parallel with this rail capacitor, the only way to determine where the fault is just to systematically remove each one of the components that you see on the path of the short circuit until it goes away. So let's see, do we have a short circuit on any of these resistors? Nope. Nope. Nicholas was right! Yeah, 1 point to Nicholas, 0 points for Sam. So I'm actually not going to bother putting these resistors back in place for now because they're only pull-down resistors, they're not important for the amplifier's operation. They just make it safer to work on once you charge the rail cap. So, okay. Nick D says it's not the cap. See, I don't think it's the cap either, but it's the next thing in the melodical line for us to be looking at. So we're going to remove it just to... the reason it's not coming out is because it's got CA glue on it. So we need to cut the CA glue off first so we can actually remove it. There we go. Now it's going to come out. All we need to do is give it a good old pull from the top. See, this glue is really sticky. They've used some nice, quite high quality glue here. There we go. Right, okay, so moment of truth then. Is the capacitor shorted? So who said the capacitor was shorted and who reckons it's the cap that's short? Place your bets now. Place bets now. So people don't think that the caps are short. So why did everyone tell me to remove the cap then? Everyone says it's not the cap, so still think that it's that ceramic near the resistors. I checked the ceramic near the resistors, buddy. It's not the ceramics near the resistors. I checked them already. It's the cap, lol, cap, neither, lol. Right, okay. So let's have a look. Is it the cap? Is it the cap? Hey! It's the cap! It's the cap! So, who said it was the cap? Who just won a bunch of money? Who placed bets on it was the cap? Oh man, this H1 Nicholas guy, this guy, man. This guy is jammy. This guy is jammy. It's rarely ever the cap, and if it's the cap, it's usually bulging or something. So, we need to dig through our donors and see if we've got a replacement capacitor for this. So, we need something that is at least the same values or better. So this is a 35 volt, 3.3, 33,000, no, fucking, I need a drink, my mouth is dry as hell. Hey, would you look at that? Would you look at that? The first caps that I pull out the drawer are the right values. They're 35 volt, 3300 UF. So just before I CA glue those in, let's make sure the amp actually works now. These capacitors have these caps have like an insulated top, okay? And these ones that are on the board now don't. So we're going to need to put some foam or some cardboard or something. Here we go, perfect. Some foam here to insulate the top of those caps from shorting out on the top of the case there. So let's put some power and see if it comes on now. Yeah, let's apply some power, and as you can see there, amplifier works fine. So we've got a good power supply wave there. That looks pretty good. Yep, nice. Looking good. And the LED for the power should come on the amplifier. Yes, we have a green light on the amplifier. And do we have rail voltage on the outputs here? Do we have rail voltage on the outputs here? Yes, we do. We have 15 volts of rail voltage on the outputs. Great success. Great success. Enjoy 100 peseos. Sorry, no NOK. That's fine for me, buddy. Thank you very, very much to Kelvin McGill for the $5. That's fantastic. I'm in the UK, so my currency is British sterling. So yeah, like any currency conversion is fine. And Travis G sends me $20. Jesus, some more PSU money. I'll definitely take you up on the ones I help when I get stuck. For sure, absolutely. I'm more than happy to help you one-to-one, especially if you donated to me, for sure. If you have any amplifiers that you need a bit of assistance with, give me a shout, and I'll be more than happy to help. Thank you very, very much to Travis G and Kelvin, and also to Love Under 86 for your very, very kind donations. That's insane. Okay, there we go, finally up and running. So clip point, let's go up a tiny bit more. There we go. That, sir, is our clip point. So if I pause the scope on that point and turn her off, so that is our clip point, and although it looks like there's only one trace here, there's actually two traces that are both overlapped on top of each other. And that's the front channel and rear channel both being driven together at the same time. So let's see how much power that did. If we have a look at our scope here on my potato camera from like 1995, we can see that we have 10.3 volts on these. Now we need to double that voltage because that was running in bridge mode. So we need to double the voltage on that to work out the power that it just did. So 10.3 times 2 is 20.6. And we need to do 4 ohms. So that just did 106 watts. 106 watts per bridged channel at 4 ohms, but that, my friends, is only at 12 volts. So our correction factor for 14 volts is 14.4 divided by 12 volts, which gives us 1.2. Times that by itself, so we square the result to give us 1.44. So 1.44 is our correction factor. So we times 106 watts times by our correction factor, which gives us 127.3 watts RMS per bridge channel at 4 ohms. So that is 63 watts or 63.6 watts per channel. Yeah, Santiago got incredibly close. I saw that comment earlier today. Yeah, man, awesome stuff. So the total watts, 127 times 2, so yeah, that did 254 watts RMS. Also, this was only at 100 Hertz, so shall we try this at 5000 Hertz now, guys, do you reckon? There we go, that's our clip point. You can see there we're just starting to clip. This is probably about 1% THD. So that was, I'm going to take 11 volts as our reference point. So we saw 11 volts with 3000 Hertz going in. This amp's getting pretty hot now, actually. Yeah, this amp's starting to heat up nicely. Per channel, that was 87. So that's much closer to its rated power. So it was rated to do about 90 watts per channel, wasn't it? At 2 ohms per channel. So running this at a much higher frequency, being at 3000 Hertz, gets this much closer to its rated power. So I think it's much happier running a higher frequency. Interesting.